Hello everyone. I'm Sebastian Sierra. I am a PhD student in Toulouse, IMP in France. And today I'm happy to present you our research related to the use of an adaptive algorithm to detect single microparticles and segmented in self-mixing interferometric signals. I will explain later about what is the self-mixing interferometric technique. So, the motivation behind this work and why this is important for us lies in the different implication of detect microparticles at a single particle level. For example, if we have a sample of water, it enables us to detect, for example, microplastics in a case of potable water. We have a sample of any body fluid. We can perform plenty of different analyses, as for example, detect cancer cells in a sample of blood. And also, this analysis also enable us to perform a different quality control. It serves as a quality control of different manufacturing chemical process. So the thing here is usually what is the more established technique to perform this case of analysis, how we can detect single particle, microparticle levels at a single particle, in a single particle point. So, the most established technique to perform this kind of analysis is called flow cytometry. This is a powerful laser-based technique in which we can extract information about cells. And usually in this diagram, you can see the main general steps. So first of all, we start with a sample, for example, of blood. We mark with a fluorescent dye the cells that we want to analyze. Then we put this sample into a microfluidic system that permits us to align all the cells in a single line. Then these cells pass through a laser beam that will cause the light scattering that we can measure with dedicated photodiodes. Then all this information is processed and analyzed, and we can extract information as, for example, the type of the cells, the size, the dimension, and so on. What is the thing? That instead that this technique is a powerful technique, it also comes with some drawbacks. So for example, if it's an invasive technique, sometimes we need to mark the cells, and to mark the cells, we can affect its behavior. And also it requires a bulky setup for the number of devices that we have in our experiments, that it results in that at the end is an expensive technique. So for that reason, there is a need to explore another innovative approach to perform this kind of analysis. So the technique that I want to present you today is called self-mixing interferometric. Basically, in the sensing scheme behind that, realizing in the fact that now we are going to use the laser beam as both for the excitation of the light and also as the detection. So basically, it's like we are going to have an all-in-one sensor. The principle behind that is that when the laser beam illuminates an external target, in our case, for example, as cells into the microfluidic system, there is going to be one part of the light that is going to be re-injected back into the laser cavity and will cause a modulation in the laser beam properties. And we are able to measure this modulation. So this is really interesting. This technique was already tested for different flow meter applications. But right now, like in my PhD, the topic is to explore how we can, with this technique, be able to detect just single particles and classify them. So here you can see the experimental setup that we assembled to perform these experiments. Basically, it comprises three different systems. So the first system is an optoelectronic system in which, I'm not sure if I can, pointer options. Yes, if you can, yeah. Here, for example, you can see our sensor and how compact it is. We have so the electronic system comprises the sensor and all the lens in order to focalize the laser beam in order to enhance the signal that we receive when one particle passes. We also have developed our microfluidic system. We create our own microfluidic chips in order to align all the particles in a single line to guarantee that we are going to classify just one particle per time. And also we have just an acquisition system in order to classify all the signals that we receive. So if we go deeper, this is, for example, the signals that I am using, the response of our sensor. So basically, in order to analyze these signals, we can make it in both, like in temporal domain and in frequency domain. So in temporal domain, we are going to have this specific modulation that can be explained using this equation model. So basically, it comprises two terms. Basically, we have one term that expresses how is the modulation, the number of bursts of fringes that we have related with the Doppler frequency of the particle, and also another term that explains how change the signal when the particle entering the laser beam and when the particle goes out. That is like this shape that we have here. And also in terms of the frequency domain, basically we are going to have is just a clear Doppler peak that is related with the speed of the particle. So what are the challenges to use this technique? Basically, it's like the signal variability. So the thing is like sometimes due to the inverse variability in our experiments, due to particles that travel at different size, different type of particles, the electronic noise, environmental noise, sometimes we can have different signals for the same type of particle. So it makes it harder to establish a clear signature of the particle that we want to classify. So in order to do that, our approach is to use machine learning models in order to enhance this classification. But the thing is that before to have the machine learning models, we need to first extract the data in order to feed the machine learning models. So to do that, right now we are working in pre-processing steps in order to just be able to segment and extract all the useful information of our data stream. So if, for example, this is a data stream with multiple particles, we want to be able to know where is located the particle and just extract this information to later pass through a machine learning model. So the algorithm that we are using right now is this one. It comprises different steps. First of all, we are considering a real-time approach because we can't miss any particle. We need to classify all of them. So for that, we just perform some numerical simulation in order to be able, in our microfluidic channel, be able to estimate all the possible range of particle velocities. And with that information, we just create a Doppler peak detection algorithm based on the frequency spectrum of our signal. So basically, every time that we have a Doppler peak, we just store all the data stream that can have one or multiple particles to then later classify them. So then, once that we have the data stream in an offline mode, we say, okay, we have one data that maybe have a particle, but we need to know where the particle is located. So for that, our approach basically was use an spectrogram and trying to evaluate how the Doppler frequency vanish over the time. So for that, the spectrograms are a powerful technique to correlate the temporal information with the spectral. But the thing is, like, sometimes the spectrogram gives us an overwhelming amount of information. As you can see here, all of that is a lot of information, where just this part, a small section, is the valuable information for us. So for that, we make another additional step in order to see, okay, in order to optimize the hyperparameters of the spectrogram based on the different possible Doppler peaks that we can have in the spectrum. So basically, it's like our spectrogram, we are able to optimize it based basically in the passage time of the particle, the possible passage time of the particle based on the speed that it has. And also certain different, and also we just analyze like the frequency range that we want to have. So at the end, it basically just permits us to pass from these kind of spectrograms to this one, where is more clearly where specifically is located the passage of the particle. So once that we have the spectrogram, we need to define, okay, the specific point at the time stamp where the particle starts and the particle ends. So basically for that reason, we just use an approach in which we just detect all the pixels that are above the average intensity of the spectrogram. And then it permits us to delimit where the signal starts and where the signal ends. And later, we just correlate that with the temporal information that we have of our signals. So we know where is possible located our particle, and we perform just a Gaussian fitting. We just perform a Gaussian fitting, knowing that usually how in our experiment all the time, when the particle enter, we are going to have like this Gaussian shape, like envelope. So we are trying to see if the modulation that we are capturing have this performance. So once that we implement all these algorithms, basically what we do is just analyze how good it is. For that, what we do is that we evaluate the passage of 10,000 of microparticles. We are working with microplastics polystyrene spheres of the range of size between 10 micrometers and 2 micrometers. So the idea was basically, okay, we just capture a lot of data based in the Doppler peak algorithm. And then we just use this spectrum algorithm just to see if our algorithm is able to extract all the different information that we have here. So we, first of all, we just observe, like we set different categories. In one of them, we say, okay, sometimes in the data that we capture, we are clear that the modulation that we have is related to one particle. So we want to know if our algorithm is able to detect that. Then we also observe that sometimes for the noise, sometimes we capture just data that only have noise, it doesn't have any particle passage. So for that reason, we also explore if our algorithm is able to target, to mark it as a like empty signal. And finally, we have another category in order, basically that sometimes in our signals, we have unclear events. We are not completely sure if the modulation that we have is related to one particle or not. So we also explore the performance of our algorithm in this, just to know, like, because maybe sometimes it can be like a misclassification of the particle, or indeed there is nothing there. So basically, like what we want to, in order to conclude, right now the thing is like, okay, we have a promising technique that is the use of the cell mixing interferometric. But the thing is like this technique, first, in order to classify the particles, we need to create like a large data set to be able to define a clear signature of that. So this algorithm permits us to increase the speed to create this database, to make it in a more robust way. And basically, at the end, the idea is just increase the reliability of this technique. And that's like the main points. So thank you so much for your attention.